Okay, I think the last one cut off, so I'm going to make dimensional analysis 2 here. Let's look at three examples that are really important. The first one, how many times will your heart beat today from 7 a.m. to 5 p.m.? Well, you're not going to put your fingers on your pulse and do that for 10 hours, but what you could do is maybe time it for maybe 10 seconds. So let's say that you time that and you find you're in pretty good shape. So in 10-second time period, your heart has beat 9 times. And so you have this kind of conversion factor that 10 seconds equals 9 beats for you. Well, we want to know how many times it will beat. So I've got 10 hours here. So let's go ahead and convert this. 3,600 seconds is 1 hour. And again, if you didn't like that one step, you could do 60 seconds in a minute and 60 minutes in an hour. But 60 times 60 is 3,600. Okay, so the seconds cancel. And now I'm just going to simply multiply by 10 hours. No conversion factor here. I'm just saying, look, I want this information for a 10-hour time period. And so I'll go 9 times 3,600 times 10, divide by 10, and you should get, something like that. And notice everything else has canceled except for the beats, and that's the answer you want. So let the units guide you to what answer you're looking for, what unit you're looking for, and the numbers will follow. Now, as far as significant figures goes, it kind of depends on how good a measuring device your clock was. So if you used the atomic clock in Colorado to do this, you probably have quite a few significant figures. If you use a cell phone, probably 2, 3, even 4 sig figs. So that one's a little hard to know because it kind of depends on your measuring device, your clock, your stopwatch. Okay, now the next one, we've got a flow rate of wastewater from a nuclear power plant, 60.0 feet per minute. So we know there's 3 sig figs there. The DNR limit, you're told, is 0.45 meters per second, and you don't want to exceed that. So say you're the chemical engineer there, and you want to make sure that you don't exceed that, because if you exceed it and the DNR knows, then you have to pay a daily fine until you get that under control. But feet per minute and meters per second, that's comparing apples to oranges, and you want to compare apples to apples. So one of these has to change. So let's go ahead and take this one right here. I'm going to take that 60 feet per minute. Now, this is something I want to bring up. Quite often with these things, you'll have a slash mark. Make sure in your work you're drawing a horizontal line. Absolutely need to do that to keep it straight. All right, well, easily enough, I'm going to go from minutes to seconds here because that's just, kind of just get that out of the way. And so 1 minute is 60 seconds. And we'll cancel. Okay, so if we were going to hours, of course, it'd be 60 minutes in an hour, but we're going to seconds, so it's 1 minute is 60 seconds. The other thing you need to know is how many feet are in a meter, and you could Google that easily enough, or look it up in your book. These 3.28 feet is in a meter. And notice, again, I have to make sure the feet, because it started up here, I put it down here. And so when I go 60.0 times 1 divided by 1 divided by 60 divided by 3.28, and you'll have your answer. Now, I will note that your calculator does get a little confused if you go 60 on the top and then you hit divided by 60 times 0.328, it will do it wrong unless you put these two things in parentheses. So if you go 60.0 divided by parentheses 60 times 3.28, you'll be fine. Or if you do them individually, if you go 60 divided by 60, hit enter and then divide by 3.28. Okay. So obviously I know some of these steps you can cancel or not have to do because 60 divided by 60 is pretty easy. But, obviously our numbers are not going to be so nice. So 0.305 meters per second. Because I have meters here and seconds here, the units I want, and I can compare these two. So obviously we are not exceeding the limit, which is good news. Okay, this last one here incorporates a couple of different issues, so I want to go through those. I'm going to start with this. I'm going to convert it And I know that 1,000 meters is in a kilometer. Got that done. I need to go from seconds cubed to hours cubed. Now, the whole concept of time cubed is probably kind of crazy, and we're going to talk about that physical reality. But right now, I'm just going to realize that 3,600 seconds is in an hour. And of course, because my seconds cubed is down here, I'm going to put my seconds up here so they ultimately can cancel. They can't cancel right now, though, because this is seconds cubed and this is seconds. I know 3,600 seconds are in an hour. So what I'm going to do, though, is I'm going to cube that second. And that's fine so that those two cancel. But you've got to cube that 3,600. You have to cube the hour. You have to even cube the one. Of course, it doesn't matter, but you cube everything within that conversion unit. So I'm going to go 3.5 times 1 times 3,600 cubed. Make sure you do the caret 3. Divided by, 1, 1,000, and 1 cubed. Okay. So definitely put that into your calculator. You're going to get like 1,632,96 something, something, something. We need to round this. I started with 2 sig figs. I don't care what the conversion units are. Those don't factor in. We just look at the measurements we were given or we started with. So this 3.5 tells me 2 sig figs. I'm also going to put that number into scientific notation because that's how all the books do it. And I have kilometers per hour cubed. Kilometers here, hours cubed down there. The only things that did not cancel. And in your final answer, you certainly can put this, but in your work, please use a horizontal line. Okay, this is a brand new way of thinking, and we are going to focus on units. And if this is giving you a little bit of grief, take heart. This is kind of a different way of looking at things, and it's really only focused on the units. So let me kind of take you through it. We've got the radius of a circle inscribed in any triangle whose sides are A, B, and C, and it's given by the following equation, in which S is an abbreviation for A plus B plus C divided by 2. And we want to check the formula for dimensional consistency. What does that mean? Well, what that means is just like our DNR problem from before, it means, am I comparing apples to apples? Okay, not apples to oranges. So I'm going to look over here on the left-hand side of the equation, and I see the radius. Now, how would we measure a radius, or for that matter, how would we measure sides? And that would be a length, right? You might do that in centimeters if it was a little triangle. You might do it in meters if it was a larger one. Just for simplicity's sake, let's call it meters. Okay, it's a length of some sort. Let's call it meters. Okay, so on the left-hand side, my answer, whatever that is in meters. Now, the right-hand side. Let's look at the S. What is S in units? What is S's units? Well, I've got a length plus a length plus a length. And when I add 3 lengths, 5 meters plus 2 meters plus 10 meters, whatever that number is, the answer is in meters. So when you add meters, you get units of meters. So S is going to be in units of meters. Now, here's a funny thing, because I think people don't like this, but does that divided by 2 mean anything for our problem here? And it means nothing. Numbers aren't going to matter. We're looking at units. So that divided by 2 means nothing to me. So I'm going to go down here into this equation. I see that S is going to be in meters. And we're going to subtract A, which is a side. So that's also going to be in meters. Now here is the rookie mistake. People look at that and go, well, meters minus meters, that's 0. No, absolutely not. If it's 5 minus 5, it certainly would be 0 if we're talking numbers. But if we're talking units, we'd be talking about something like 10 meters minus 5 meters, and the units would be meters. So what we're really looking at is the square root of meters. In the same sense, I'd have meters times meters. So each of these terms are going to be measured in meters. And then I'm going to divide by meters. Now, we know that if we take a length times a length times a length, we get a volume, right? Meters cubed. And we still have a length. If I take a volume divided by a length, meters cubed divided by meters, I get meters squared. And if I take the square root of meters squared, I get meters. So the right-hand side of the equation, the units will be in meters. The left-hand side will be in meters. The formula is dimensionally consistent. Another example of this would be the universal gravity constant, and that number, we'll use it in calculations, but let's focus in on the units here. And in physics, it's probably the first time that you've got units that are just kind of crazy. You know, for one number, you've got all these units, but they make the physical reality work. What would I get if I took this, and again, I'm going to write that horizontal line rather than the slash. I'm going to multiply it by kilograms over meters. Well, what would happen is this meter squared would cancel. I'd get 1 meter on top. This kilogram, and I would get Newton meters over kilogram. Now, what if I took that and divided by newtons? Okay, well, that would be the same thing as if I took Newton or 1 and flipped it and did that. Okay, so either way you want to do it, I would be left with meters per kilogram. Okay, that's just focusing on the units, and then you drag the numbers along with you. Lastly, I just want to point out a little bit of trig review. Make sure that you are really up on the trig. Say it over and over, even though you know SOHCAHTOA, you know. Make sure that you really, because we're going to go through this fast, we use it like we know how to add 2 plus 2. We use the SOHCAHTOA, so just kind of make sure that you are aware of it. Example of how we use this is, let's say that we want to know how tall a building was, or maybe a roller coaster if we go to Mall of America, or if we go to Valley Fair. And we want to know, we're going to calculate some physics stuff, and we need to know how tall that roller coaster is. Well, this is a very rough estimate, of course, but I don't think we're going to drag out all the, you know, all the equipment to get the exact answer. So let's say that you're standing on the ground 70 meters from the base, and you want to know how tall that is. And we use these little devices that, it's a protractor basically with a little string hanging down. And this is going to be used a lot in physics. So not just when we go to Mall of America, but we're going to draw a little right triangle. And anywhere we draw that little right triangle, I could have drawn it up here at the top. Anywhere you draw it. This angle right here is the same as that angle right there. So when we measure, we'll hold up the little protractor to the top of the building. We'll let the string hang down. We'll measure the angle, and we know that this theta and this theta are equal angles, and we use that a lot. We use the fact that this little right triangle is here too, and use that a lot in calculating things. All right, so in any case, you can probably just use the tangent here would be the opposite over adjacent. So opposite over adjacent, which is our 70. And this is the height. The opposite is the height that we're looking for. Wow, that is not doing so well. Okay, opposite there, the height. And then you can tangent of 32 times 70 is equal to our opposite, our height. Okay. So those are some real basic things that we use. So go over this, make sure you understand everything, practice it, and then you'll be ready to do some physics.